After we are happy with our model estimation, it's time to put the model in use. One of the most important applications of time series analysis is forecasting. So we estimate the future value of y based on the model that we estimated. So on this slide, we start off with an AR model. The example is real GDP growth, and we have an AR2 model. So if we look at the equation on the slide, we have the lagged terms of the dependent variable or real GDP growth only in the right-hand side. So that's lagged 1 and lagged 2 terms. So we have the correlation coefficients correspondingly. And the two most recent observations are in the third and the second quarters of 2009. So we can make use of those information to forecast the quarterly GDP growth rate as follows. So the next quarter is the fourth quarter of 2009 by inserting those two observations, 0.8 and minus 0.2, into this equation. We obtain an estimated quarterly real GDP growth rate of 0.7181%. Then we move to the next quarter. That's the first quarter of 2010. Now we need GT and GT minus 1 in order to estimate the value of this real GDP growth rate. And you may notice that we use 0.8, which is the value of GT minus 2. And now we use 0.7181, which is the estimated value of last quarter's growth rate in this equation, because that's the only information that we have. We run out of observed value when we step into the next quarter. So when we estimate the value for the next quarter, the estimated value of previous quarter's growth rate are both estimated. One is from the first estimation, the second is from the second estimation. So you may realize that this type of time series analysis are not going to be very accurate if you make a forecasting quite further down the road, because you're going to make use of a lot of estimation in the whole process. So this is how to make an estimation or forecasting based on an AR2 model. It's useful when we need to estimate a value of a variable without any other information except for the historical values of the variable itself. So we use this AR model. And we can also estimate the confidence interval, or 95% of a confidence interval for the forecast. In order to calculate the confidence interval, we need to know the critical values from the table and the standard deviation. The standard deviations can be estimated by using this formula. Here, theta 1 and theta 2 are simply the correlation coefficient corresponding to GT minus 1 and GT minus 2 on the previous slides. The good news is software can calculate those standard deviation and the forecast intervals quite efficiently for us. So we have the forecast over there. That's the estimated value based on the calculation on the previous slide. Then we can calculate the forecast intervals for each one of them. This do not look good because they are quite wide. You may notice that 0 actually is within the range, and it runs from a reasonably large negative value to a large positive value. That's quarterly GDP growth rate, by the way. So 1.8 is not a small number. So those estimation intervals basically tell us the forecastings are not that accurate. The interval is pretty wide. So that's the conclusion we can draw from this set of estimation. The next example is based on a more general model. So it's ARDL model. We have the lag terms of both the dependent and independent variable, as we shown here. So that's Occam's law, ARDL11 model. And we can estimate the value of GT plus 1 based on the discussion that we had before on the last two slides. So if you need the future value of GT plus 1 in your ARDL model, this is how you can do it. As a sidebar, if you need to estimate the value of ut plus 1 instead of just du, and you have this type of a specification, you have the difference of a du, you can rearrange the model. So for example, here, ut plus 1 minus ut is simply dut plus 1. And here, that's ut. So ut minus 1, that's ut. So this is the same equation as the first one. Then you rearrange it, you may notice that, okay, I actually can base on all the historical values of ut and gt and an estimated value of gt plus 1 to estimate or forecast the value of t plus 1 by using this formula. In other words, an ARDL11 model for a change in a variable, that's dut plus 1 by the way, can be written as an ARDL21 model for the level of the same variables as shown over here. So this is what we are talking about here. Okay, so because you have a t and a t plus 1, a t minus 1 in this equation, so the lag term is 2. Okay, that's what it's talking about. That's just a sidebar in case you may need to estimate the value of ut plus 1. It can be done by using this formula. The next way to do forecasting is to use exponential smoothing, which is quite commonly used in practice. And the benefit of using it is it doesn't require other information than the historical value of the variable itself. So it's similar to AR1, but it's easier to implement. It's based on the idea that it's a more general form of a moving average. A moving average puts equal weights on all the current and historical data point that you have. So for example, here, you use the last 3 periods variable values to calculate moving average and to forecast. And you may notice that the weight on each historical variable observation is 1/3. And if you want to assign different weight, or specifically you want to put more weight on more recent observation, and you want the weight to decline exponentially as the observation gets old, which is quite intuitive, you may consider this type of specification. So we use alpha to control the weight on all of those historical observations. And based on this calculation, this equation, the weight will decay over time. And mathematically, we can demonstrate that the summation of all the weights equals 1. They sum up to 1, which satisfy the criteria of a weighting system. And with a little bit rearrangement, this equation can be turned into this. It has a very good intuitive explanation that basically means the forecast, 1 period ahead of forecast, is a weighted average of the observed value and the estimated value from the last period. And the weight is controlled by this alpha. So the determination of this alpha or smoothing parameter is quite important because it controls the distribution of weight among all the historical observations that we have. Generally speaking, the smaller the alpha, the smoother the forecasting line, because we basically put roughly a more evenly distributed weight among all historical variables. If the alpha is quite large, that basically means we put a lot of weight on the most recent observation, and the estimated variables tend to be quite close to the most recent observation. And as a result, the estimation will not be that smooth. We're going to have some visual demonstration later to show the effect. Then the question is how to determine the best value of the smoothing parameter. The common practice is to find the value that can minimize the sum of squares of the one-step forecast errors. So it's quite similar to the rationale behind OLS. We find a value that can give us the best forecast result, then we go with it. And the forecasting formula, of course, is like this. So you just need to find out, what's the value of alpha through this process? What is the observed value in the last period? And what is the estimated value from the last period based on my estimation? Then you can make a 1 period ahead forecasting based on this formula. So on this slide, I use some example to show to the effect of different smoothing parameter. So on your left-hand side, the first diagram used an alpha of 0.38. So that's the exponential smoothing at forecasting of GT. Right-hand side is still the same set of data, same variable, but the smoothing parameter is 0.8, which means we put a lot more weight on the most recent observation. So if you look at the dotted line, which is the estimated or the forecasting, 1 period ahead forecasting based on the two different smoothing parameters, you may notice that the first one, in the first chart, the line is smoother than the second one. And you may also note the smoothing parameter can have a significant impact on the estimated value of GT plus 1. Notice that when alpha equals 0.38, the estimated quarterly growth rate is 0.05%, quite small. And if we use 0.8 as the smoothing parameter, the quarterly GDP growth rate is much larger. It's 10 times of the estimation when we use a smaller smoothing parameter. So the choice of a smoothing parameter is quite important. It can significantly affect the result. And we use this we minimize the one step ahead forecasting error to find the best smoothing parameter. The good news is, in most, if not all, statistical softwares, you will have an algorithm built in to help us to find this smoothing parameter.